Welcome back, everyone. So we're going to continue on with Chapter 1, our Introduction to Biology, from our OpenStax textbook. So this video, we're actually going to switch gears. So we've been kind of talking about an overview of biology, learning about the scientific method and the properties of life and things like that. But now we're going to kind of narrow our focus into a little bit of chemistry. So we're going to start taking a look at the building blocks of molecules in section 1.4. So by the end of this video, you should be able to describe the structure of an atom, as well as describe how several bonds arise from the interaction of atomic particles and resulting charges on elements. Okay, so this is, quite different from what we've been talking about so far. Okay, so we've been kind of, focusing on living things, and now we're looking at atoms, okay, the smallest units of matter. So this is kind of a big change, but we need to know what atoms are, and we need to know how atoms form molecules in order for us to learn about chemical reactions, and then those will then further allow us to understand how those chemical reactions learn to arise, to describe metabolism and energy processing, and hey, that's a property of life, right? So, some of those complicated things that we're going to further learn about further in the term. So we're kind of going down to the foundation, and then we're going to build up from there. So we've talked about life's hierarchy, where we learned that cells are made of organelles, and organelles are made of macromolecules, and macromolecules are made of molecules. And what are molecules made of? Atoms. Okay, so atoms were like that smallest unit of life's hierarchy. And in our description of an atom, we stated that atoms are units of matter that, maintain the chemical properties of an element. But we never really defined what matter or elements are. So here's the definition. So matter is any substance that occupies space and has mass. Okay, so air actually is made of matter. Okay, so we have little oxygen atoms, and actually oxygen molecules. They're two oxygen atoms stuck together, floating around. We have nitrogen gas, which is two nitrogen atoms stuck together, nitrogen molecules stuck together, floating around. So that has mass. We have carbon dioxide and carbon monoxide, and ozone, that's O3, that's three oxygen atoms stuck together. So all of that is, floating around in the air surrounding us. And all of that actually has mass to it. So even the air that we breathe is made of matter. Okay, so anything that occupies space and has mass is made of matter. Okay. And then I keep throwing out those terms: oxygen, nitrogen, carbon, all of that, those are elements. So what are elements? They're just unique forms of matter with specific chemical and physical properties that cannot be broken down into smaller substances by ordinary chemical reactions. Okay, so just like we like to classify our different organisms into specific species, we classify our different elements based on their specific chemical and physical properties. So an oxygen atom is, it has a specific chemical physical property that is different than carbon, and that's different from nitrogen, and that's different from hydrogen, and so forth. Okay. All right. And since we're talking about living things are made of matter, and so that's why we're focusing on that. All right. So speaking of elements, if we take a look at the most common elements in your body, the majority of those elements, actually the most common element that's found in your body is actually oxygen. So 65% of your body mass is oxygen. Okay, that's pretty significant. And that includes water. H2O, right? And this is body mass, okay? So oxygen is actually a heavier atom or element than hydrogen, for example. And then carbon is another significant part of your body, okay? And then hydrogen, nitrogen. I think in the if you look at your class objectives, like those notes, I think it has you list 6. So you can list all 6 there. So oxygen, carbon, hydrogen, nitrogen, calcium, and phosphorus. So those are the top 6 elements that make up you. Okay, so you are mostly just 6 elements. Okay, so and if you look at the percentages, if we added up those percentages, it would pretty much be 99% would be oxygen, carbon, hydrogen, nitrogen, calcium, and phosphorus. That's it. You're pretty much just made of 6 elements. Pretty significant amount. Okay. Now. And then you can see some of the other ones that are also pretty important, like potassium and sulfur and sodium and chlorine and magnesium. So they round out the other, 11 do we have total up there? Something like that. All right. And again, just look at the first 6. You don't need to memorize everything there. Now at the bottom of this list, we have something called trace elements. Okay. So I believe there's 35 naturally occurring elements, and we need like 23 of them, and so some of them we just need in very, very minute quantities. Okay, so those are called trace elements. So trace elements are just need in very, very small amounts, less than 0.01% of our mass, okay? And so those would be, here's a list of examples there. So boron, chromium. Actually, I've seen chromium supplements on the market for some reason. Cobalt. That's a, pretty color blue, right? But you don't want to take too much because then you turn blue. No, just kidding. Copper, again. A lot of these you can think of as if you have too much, it could be poisonous to you, right? So copper, you don't want to have too much because that's a metal. Iron, a lot of people have too little of it and you get anemic, but you can also have too much and have get poisoned from it. Fluorine, iodine, manganese. Okay, so all of those are examples of what we call trace elements. So you just need them in small quantities. You don't need too much of them. But sometimes people are missing one of these trace elements from their diet, and or from their, if they don't get enough in their diet, then it actually can cause a lot of issues. So again, what happens if you don't have enough iron in your diet? You can become anemic. And, women in particular tend to suffer from anemia a lot more often than men. So with anemia, what are some side effects of that? You're tired, and just you can't really do as much. You're low energy because of that. Iodine. Some people if they lack iodine, they end up getting a goiter, which is this kind of big growth in their neck. So their thyroid is it's an endocrine gland that is in your neck. It's this butterfly-shaped gland in your neck, and it actually regulates a lot of hormones. And if you don't have enough iodine, it actually will start to expand. And so people that don't get enough iodine, they get these goiters, and that can be kind of troublesome and things like that. And so that's why you do see like iodine has been supplemented in a lot of items. Like if you've seen at the grocery store, if you buy salt, salt has been iodine added to it so that we get extra iodine in our diet. Okay, so some of these, you just take a multivitamin and you're fine, okay? But yeah, a lot of it, you can just get from your normal diet. All right, so we've talked about matter, we've talked about elements, we've defined them. So now let's talk about the smallest unit of our life's hierarchy, the atom. So the atom is the smallest unit of matter, we know what matter is, that retains all of the element's chemical properties. So we can talk about an atom of oxygen, or an atom of carbon, or an atom of hydrogen. Okay? Now when we look at an atom, anything smaller than an atom we don't consider a unit of an element, just because it doesn't have all of the chemical properties in there. But we can define what are called subatomic particles, so things that are make up the atom. So if you look in the middle of this picture here, this atom here, this is a helium atom. And in the middle, we call that the nucleus, just like, in the cell. The nucleus contains two subatomic particles, the protons and the neutrons. And the protons, they have a positive charge, so their electric charge is positive, and then the neutrons have a neutral charge. Okay, so they're no, they don't have a charge. And then the electrons, they are electrically negative, so they are circulating around the nucleus in an orbit. Okay. So that is our atom here. And then here's just a chart that kind of summarizes. So protons, neutrons, and electron are the subatomic particles that make up our atom. And you can see, we talked about the location. So protons and neutrons, they hang out together in the nucleus. And then the electrons, they are circulating in the orbit surrounding the nucleus. Now, as far as the mass is concerned, electrons, they don't really have mass to them, okay? So their mass is so small it's negligible. And so we quantify protons and neutrons as having each one atomic mass unit. So that's what that AMU stands for. So AMU stands for atomic mass unit. So one proton would be, the mass would be one atomic mass unit. So two protons would be two atomic mass units. All right. Now before, in the second to last slide, this slide, I said that this is a helium atom. Now the reason why I know it's a helium atom is because there's two protons there. Okay, so the element's atomic number is defined by the number of protons. And I know if I looked up the periodic table, the atomic number 2 belongs to helium. So helium is basically has two protons because its atomic number is 2. So the atomic number is determined by the number of protons. So oxygen, its atomic number is 8, so it has 8 protons. It will always have 8 protons. It will never have 9 protons. It will never have 7 protons, okay? If it had 7 protons, then it would be a different element, okay? It would be, is that fluorine? I can't remember, okay? So the element's atomic number is determined by the number of protons, and that never changes for that particular element. Okay, so carbon is always going to be atomic number 6 with 6 protons. Helium is always 2. Hydrogen is always 1. Okay, so when you look at that periodic table, you look up the atomic number, that's always going to be the number of protons for that element. Okay. The number of protons does not change for the element, but the number of neutrons can vary, okay? So we don't automatically assume that there's going to be equal number of protons to neutrons. So there might be differences. And so when there's differences, we call those different atoms isotopes for that element. Okay, and I'll give you a couple examples. So for now, let's just keep that aside. but just recognize that for an element, they will always have the same number of protons, but they can have different number of neutrons. Okay? Next, let's talk about the mass number. Okay, so the mass number is the number of protons plus the number of neutrons. Well, what about the electrons? Remember, we don't count the electrons because their mass is so small, it's negligible. Okay, so we only count the number of protons and neutrons. So if we take an element and we add up the number of protons and the number of neutrons, we get the element's mass number. Okay, so if I counted up, let's say we have, go back to the slide before, we have helium here. We have 2 protons and 2 neutrons. Okay, so its mass number is 4, right? So pretty simple. All right. Now, if I look up the mass, or if I look in the periodic table, instead of having the mass number, you might see an atomic mass. So atomic mass is basically, instead of having like a whole number, it's usually a number with, decimal point and to the hundredths or something. And so that's called the atomic mass. So the atomic mass is an average, okay? So it's the calculated mean of the mass number for its naturally occurring isotopes. Okay, so for the elements, the elements, there's a number of different isotopes of those elements. And so that means there's a number of different mass numbers for that element. And so on the periodic table, basically they just calculated the average mass number to get the atomic mass. Okay, so for example, chlorine, if I looked it up on the periodic table, chlorine, its mass number is 35.45. But if I calculate that out, okay, I know there's 17 protons, but it can't have, 18.45 neutrons. That's impossible, right? So that means that they calculated it as a average, okay? So for example, that's just an average of all the different isotopes. And here's an example of an isotope, okay? So here we have chlorine 35. So here in chlorine 35, we have 17 protons, so that's its atomic number, same as this one, but there's an extra neutron, so 18 neutrons. Chlorine 37, there's 3 extra neutrons. So these are different isotopes of the element chlorine, okay? And so this explains why we have this weird number here. Instead of just 17 protons plus 17 neutrons equals 34. We don't have a whole number, okay? So we have basically an average of all the naturally occurring isotopes. So we're gonna have a different number than that, okay? So just, that's why it's a little bit different on the periodic table. All right, so again, here's our definition of isotope one more time. So isotopes are different forms of an element that have the same number of protons but different number of neutrons. So one thing that's helpful with isotopes, we can actually use our understanding of isotopes in biology, particularly in fossils, to date fossils, to figure out how old they are. So isotopes, some isotopes are actually radioactive, which means that they can emit neutrons or protons or even electrons in order to basically drop down to a more stable form. And so we call those radioisotopes or radioactive isotopes. And so we can use that to our advantage. So for example, each one of us has carbon-14 in our bodies. So carbon-14 is an isotope of carbon. So carbon has 6 protons, and so its most stable form has 6 6 neutrons. Okay, so 6 plus 6 equals 12, but this one has 14, so that means it has 8 neutrons. So in this case, carbon 14 will actually decay to nitrogen 14. Okay, so it undergoes this process where it will actually, in this process, it will gain a proton, and in doing so, it will lose some energy. And so, and it does this, it has a half-life of about 5,730 years. So we can actually figure out how old a fossil is by figuring out the ratio of carbon 14 to nitrogen 14. Okay, and by doing that we can figure out how old it is. Okay, so it's helpful in dating things, and we can actually use other radioisotopes to date even older things. So there's like potassium, I think it's like potassium 40 or something like that. I can't remember off the top of my head the different isotopes, but it just allows us to kind of compare how much of of that isotope is present in the fossil compared to what the more stable form it is, and that'll give us an idea of how old it is. Okay, based on the half-life. All right, so radioisotopes can be helpful. They're also helpful in medicine, so because some of them have, they can show up because a lot of them, they give off energy, right? So, they emit neutrons, protons, and electrons. They can actually glow in certain settings, and so they can be used in medicine to like highlight when cells are actively dividing. So they can be used to like determine if there's a tumor or, cancer or things like that. Okay, so here is that periodic table I keep telling you about. So the periodic table is something that you don't have to memorize because it's there for you to just be able to read off of. Okay, so you just need to know how to read it. So you can see how it's organized. So we have 1 over here, so that's the atomic number, and then here's the atomic number 2, 3, 4, 5, 6. So you can see how it's kind of arranged going from left to right, 3, 4, 5, 6, 7, 8, 11, 12, 13, 14, 15. So we're in these rows. And if we look closely at each of the boxes, so here's a box that's been highlighted. There gives you, 4 pieces of information. So you have the atomic number, which is the number of protons. You have the symbol of the element. So that's easier to write down than the whole name. Okay, so it gives you the name, but when you're, writing a chemical formula, it's easier to write an H than the whole word hydrogen. And then it also gives you the atomic mass. And remember, the atomic mass is, the average of all of the isotopes. So look at this atomic mass, 1.008. So that tells you something there. Okay. How many neutrons does hydrogen normally have? Probably none. Okay, because its atomic number is 1. It always has 1 proton. But hey, look at that. It probably doesn't have a neutron. So that's kind of interesting. And I'm not, you can see some of the other ones are kind of, you can see what their atomic numbers, none of them has a whole number there. All right. Oh, except for oxygen. Oxygen 16.00. So there's 8, it always has 8 protons and 8 neutrons. Okay, so it's pretty solid there. All right. Another thing that you, looking at this periodic table, and we'll get into it in a minute, is that it is useful in figuring out the location of these elements in order for us to predict which element is more likely to react with whom. Okay, so if you look over here on the far right, this number 18, or I guess column 18 group, You may already know what this group is called. These are the noble gases. These guys, they are non-reactive. So that means that they're not going to want to react with anybody over here. Okay, so they are very, very stable. Okay, so helium, it's stable. It doesn't want to react with anybody. Neon is stable. Argon is stable. It doesn't want to react with anybody. Okay, so, and we'll go more into detail of like, you know, what's stable and, you know, the reactions are in a bit. But first, let's do a couple review questions, okay? Just to make sure we're understanding the atoms and elements themselves. Okay, so magnesium has an atomic number of 12. Which of the following statements is true of a neutral magnesium atom? Is it, it has 12 protons, 12 electrons, and 12 neutrons. It has 12 protons, 12 electrons, and 6 neutrons. It has 6 protons, 6 electrons, and no neutrons. Or it has 6 protons, 6 electrons, and 6 neutrons. So which one of these is correct? All right. So right away we can eliminate 2 of them, right? So magnesium has an atomic number of 12. So atomic number is the number of protons, right? So that means that it can't be either of the bottom 2 answers, right? Okay, so it has to be either of these. Now, if we continue on, which of the following statements is true of a neutral magnesium atom? So what does neutral mean? It means neutral charge. So that means that it's not a positive or negatively charged atom. Okay, so it has, that basically means it has equal number of protons to electrons. Okay, so that means both of these have equal number of protons to electrons. Okay, now both of these have that, but which one do you think would be most plausible? Okay, would it have 6 neutrons, half as many as electrons and protons? Probably not. So this one up top is the correct answer. Okay, so having half as many neutrons, usually it has more neutrons, not less. Okay, for an element, definitely not half as many. So this top answer is the correct one. All right, here's another review question. An isotope of sodium, which its symbol is Na, has a mass number of 22. How many neutrons does it have? If you said 11, I would agree with you. So how did we figure that out? So we had to look up the atomic number for sodium. So here's sodium. Its atomic number is 11. So if its atomic number is 11, we know the number of protons. So 22 minus 11 is 11. Okay. Okay. So let's get into, so we've talked about atoms in detail and what they're made of. So now let's move up on our life's hierarchy. So remember, if we put 2 atoms chemically bonded together, we get a molecule. And molecules bonded together make macromolecules. And macromolecules form organelles. And organelles form cells. Okay, so we're going to move up the scale there. So now we're going to, again, here's the definition of a molecule. So molecules are 2 or more atoms chemically bonded together. So what does that mean, chemically bonded together? That means that they are going to react to each other in the sense that they're going to have electrons orbiting, and they're going to there's going to be a chemical reaction involving those electrons, or the electrons are going to bond the 2 atoms together. Okay, so in order for us to figure out which of these elements are more likely to form molecules with each other, we have to figure out their electrons, what their electrons are doing. And so we have to look at a couple of rules. So the first thing is, we know that the electrons are orbiting the outside of the nucleus, but there's certain rules that involve the orbits. Okay. The first thing is the electrons, they circulate in what we call shells, and there's different shells. So the first shell, it can hold a maximum of 2 electrons. So that innermost shell that's closest to the nucleus can only hold 2 electrons, a maximum of 2 electrons. Okay. So for hydrogen, it only has 1 electron if it's neutral. And so it only has 1 electron circulating its nucleus. And so it can have a maximum of 2, but it only has 1. Helium has a maximum of 2 electrons orbiting its shell, and it only needs 2. Okay, it's filled. That's why, again, like I said before, the ones over here are non-reactive, because it doesn't need any more. Its orbit is filled. Its shell is filled. Okay, so these guys, their shells are filled. Hydrogen, it has 1 electron, but it still needs 1 more to fill its shell, so it wants to react with another atom or to be able to fill its outermost shell. Okay. If we look at something like lithium, it has 3 electrons. Okay, so protons and electrons are usually equal if it's a neutrally charged atom. So its first 2 electrons fill the first shell, but then we have another shell. So the next shell can hold a maximum of 8 electrons. So the lithium, it has 1 electron in its outermost shell, but the outermost shell can hold 8. So it needs 7 more electrons to hold it, to fill its outermost shell. So this guy is, has a lot to live up for, right? Okay. If we look over here at neon, neon has 10. So 10, the first 2 electrons go in its first shell. The next 8 fill the outermost of the second shell, and so that's completely filled. So neon is happy and non-reactive. But fluorine has 2 filling the first shell and 7 filling the outermost shell. So 7, that means that it just needs 1 more electron to fill its outermost shell. So, if only it could get that 1 electron that lithium has. So you can start seeing here that these atoms can kind of work together. So, lithium could probably get rid of its electron and drop down to its first shell. And by doing so, it would be something called an ion, and we'll talk more about that in a minute. But in order to, be in its happy state, okay? Fluorine could gain that extra electron, fill out its outermost shell, and be in its happy state. So you can start seeing how these atoms, they can kind of interact with each other to form molecules and bond. So they're sharing their electrons, or they're giving up or exchanging electrons. Okay. So that first shell, the shell closest to the nucleus, can house maximum of 2 electrons. And the next shell can house a maximum of 8 electrons. When we get down to these guys, the third shell, they can house a maximum of 8 electrons. When we move past that, we get a little bit more complicated. Okay, so we'll just go to the third shell in this class. Okay, so that's the octet rule. So that just states, with the exception of the innermost shell, which is the shell with 2 atoms are more stable energetically when they have 8 electrons, okay? And we call their outermost shell their valence shell, okay? So the valence shell is just the outermost shell, right? So a couple more terms there for you. So when we're talking about this column here, I guess it's called a group. The group 18, they are the highly stable group because they filled their valence shells, and so they are considered inert or non-reactive. They're also known as the noble gases. So neon, it's filled its outermost electrons, so it's not going to react. You know, if nitrogen wants to react with it, you know, why? Why would neon react with nitrogen? Nitrogen wants, you know, a couple more electrons, 3 more electrons, but neon doesn't want to give any up. It's stable, it's happy. Okay, so it's not going to react with nitrogen. Okay, so these are the stable guys over here. Groups 1 and 17, so this column and this column are more likely to form ions. So ions means that they are more likely to want to gain an electron or lose an electron to fill their outermost shell. So again, lithium, remember lithium has filled its innermost shell with 2, but then just has 1 electron in its outermost shell. So it wants to lose that electron, and by doing so, drop down to the innermost shell as its valence shell. And if it lost an electron, it would have 3 protons, but only 2 electrons. So it would have an extra proton, which is positively charged. So in that case, it would be a positive ion. Fluorine would love to gain an extra electron because it has 7 electrons in its outermost shell. And if it gained that extra electron, it would have 8 electrons, or actually it would have 10 electrons total because it has 2 in the innermost shell, to its 9 protons. So it would have an extra electron, making it a negative ion. Okay, so those, so just by looking at this periodic table, you can already start predicting what, you know, which would react with whom. Okay, and you know what they're more likely to do. All right, so next we're going to talk about chemical reactions and molecules. So we know that, you know, most of those elements are not going to have enough electrons to fill their outermost shells, so they're going to need to have a chemical bond. So there's different ways that they can do it. We talked about one way is to either gain or lose an electron. Okay, so that's one way. So they can gain that electron and become an ion, or lose an electron and become an ion. They could also share the electron. Okay, so when 2 or more atoms chemically bond with each other, the result is a molecule. So if they're, you know, if they're giving or gaining or losing an electron or sharing an electron between each other, they're forming a chemical bond. Therefore, they're becoming a molecule. Okay, so here's an example. Here's sodium. So, and by the way, these are good representations of, you can see the electron configurations. So here's sodium. So sodium, I believe, has 11 electrons. So we have 2 in its innermost shell, and then we have, sorry, it's up here, 2 in its innermost shell, and then it's filled its second shell with 8, and then its third shell, it just has 1. Okay, so it really wants to get rid of this one to drop down. Okay. Chlorine, I think, has 17, something like that. So here it's filled its 2, it's filled its second shell with 8, and then it has 7 in its valence shell. And so it just needs 1 more to fill that third shell. So it really wants to gain that extra electron. So if they work together, and form a bond, a chemical bond, then sodium can drop down to its second shell and be more stable. Okay, and chlorine can gain that extra ion to fill its outermost shell and become more stable. Okay, so by donating and accepting electrons, they form a bond together. Okay, and by doing so, sodium will be, positively charged ion, chlorine will be negatively charged ion. So they'll form what's called an ionic bond, and we'll get to that in a minute. Okay, so they'll be forming chemical bonds for each other, and so they will become a molecule. All right, so with our ions, as I stated before, ions are when we gain or lose an electron. And they have special names, particularly if they've gained an electron. They are what we call an anion. So an anion means that they've gained an electron, so they have a negative charge. And then if they have a positive charge, meaning they've lost an electron, they are a cation. So sodium there is a cation. Chlorine would be the anion. Okay, and then as that electron's moving from the sodium to the chlorine, we have that electron transfer taking place. And now we have that sodium and the chlorine together forming an ionic bond. Okay, so that's two ions of opposite charge bonding together. Now this type of chemical bond is considered a weak bond because, at this point, the sodium has already kind of given its electron to the chlorine, so, they're just kind of weakly bonded together. So, they'll kind of hang out, but they're not married. They're not, living together forever. They'll just, be friends for a while. Okay, until something better comes along. So they have a weak bond. All right. So, and an example of an ionic bond, these type of molecules, these are typically called salts. So NaCl actually is salt, table salt. So if you think of table salt, what happens to table salt when you add it to water? It dissolves. It separates and you don't see sodium and chloride together anymore, okay, and it separates. So sodium and chloride together form an ionic bond, but it's a weak bond, okay? All right, moving on to another type of reaction. So sometimes it's impossible for a molecule an atom to simply give up electrons or to gain electrons. So instead, they have to share them. So let me go back to the periodic table. So let's look at carbon. Look at carbon. Carbon has 6 protons. So that means 2 fill its innermost shell, and then it has 4 in its valence shell. 4. It cannot get rid of 4 electrons. It cannot gain 4 electrons from anywhere. So the only way that it can fill its outermost shell is by sharing, okay? So sharing electrons, that means that they're going to be forming covalent bonds. So covalent bonds are sharing electrons between 2 atoms, 2 or more atoms. Now we have 2 types of covalent bonds. I'm actually going to start with the one down here. We have a nonpolar covalent bond. So a nonpolar covalent bond means that they are equally sharing the electrons. So here we have our carbon. Remember, carbon has 4 valence electrons. So it 4 electrons in its valence shell. And then remember how hydrogen has 1. So hydrogen wants 2 to fill its outermost shell. So what it can do is it can share its electron with carbon, and carbon can share its electron with hydrogen. And so by sharing those two electrons between each other, they can help fill their shells, right? And in this case, it's an equal sharing of electrons. Okay, so that means that, you know, there's an equal time spent for that single the two electrons that they're sharing between each other, equal time spent in hydrogen's orbital and carbon's orbital. All right, so equal amount of time. Same with this sharing, this group of sharing, this group of sharing, this group of sharing. Okay, so this is an equal sharing of electrons. All right. In a polar covalent bond, we have something that's unequal, an unequal sharing of electron. Okay, so this has to do with one atom being more electronegative than another. So you don't really need to memorize which is more electronegative than the other. This is not a chemistry class. But just know that oxygen has a higher electronegativity than hydrogen. I believe oxygen's electronegativity is 3.5, whereas hydrogen's like 2.1, something like that. Okay, so because oxygen's electronegativity is higher than hydrogen's, the electrons are going to be more attracted to oxygen. So remember, oxygen has 8 electrons, so 2 fill its innermost shell, and then it has 6 in its valence shell. Hydrogen has 1. Hydrogen has 1. So yeah, so they're sharing 2 here. They're sharing 2 here, but because of oxygen's higher electronegativity, the extra hydrogen electron here is going to more often be in oxygen's orbit. Okay, it'll occasionally go back into hydrogen, but it'll more often be in oxygen's orbit. And so that leads to this kind of unbalanced molecule here. So if I look at this entire molecule and I look at its gradient of electronegative, you know, it's a positive and negative charge, this side of the molecule is going to be slightly negative because there'll be electrons more often over here, and on this side, there'll be less time that there'll be electrons there because they'll be most likely circulating the oxygen. Okay, so there'll be a slight positive charge on this side and this side of the molecule. Okay, so that is due to the polarity of this particular molecule. So polar covalent bond is formed when we have an unequal sharing of electrons. So the oxygen hogs the electrons. Well, it doesn't really hog it. It's just the electrons are more attracted to the oxygen than the hydrogens. So the electrons spend more time in the oxygen's orbitals. Okay. Over here you see we can have a double bond, so that means that 2 pairs of electrons are shared between the 2 oxygens. So remember, oxygen, it has 6 valence electrons in its outermost shell, so it can actually share 2 sets of electrons between each other, and since they are each the same electronegativity, they're equal, so it's a nonpolar covalent bond. Okay, so they're equally sharing those electrons between them. And we denote a double bond, so there's 4 electrons being shared here with the 2 lines, whereas a single bond, just 2 electrons shared there with 1 line. All right. Now these particular bonds are very, very strong. So covalent bonds are really strong because if oxygen loses its electron from, you know, that electron it's sharing with hydrogen, then suddenly its outermost shell is not filled, you know, and it can't share it anymore. Okay, so it's going to hold on to hydrogen as close as it can get to it. Okay, so it really wants to hold on to that bond. So covalent bonds are really, really strong. Ionic bonds, they're pretty weak. Covalent bonds, they're super, super strong. They're hard to break. Okay, and then moving on to a couple other types. So these are a little different because they're not really forming molecules, they form between molecules. So hydrogen bond is an interaction. It's not it doesn't form within a molecule. It forms between two molecules. So remember how hydrogen can be have a partially positive end when it's in a polar covalent bond. So remember you have this oxygen that's kind of taking the electrons, and so it's kind of partially negative over here, and then you got partially positive over here. Well, because it's partially positive over here, that hydrogen has a, kind of an attraction to the negative end of this oxygen over here. And so it can form a temporary bond with this oxygen. And so we call that a hydrogen bond. So hydrogen bonds are temporary weak interactions between the partially positive ends of the hydrogen of one molecule and the partially negative ends of a nearby, more electronegative atom of another molecule. Okay? So this doesn't happen between two atoms. It's not happening within a molecule, it's happening between two molecules. Okay, so this is not a permanent thing. It's a temporary bond. All right, so these are very weak. Covalent bond, very strong. And then van der Waals interactions, they're very weak interactions between molecules, and they just happen when there's temporary charges attracting atoms that are very close together. So if you think of how if you've ever been to a tropical place and you see like geckos crawling, walking up the side of the wall, and they can kind of cling to the wall, which is kind of cool. Well, those little hairs on their I think they're called papillae on their fingertips, their little digits. They actually can form these temporary bonds with the wall, and just that brief interaction can form a very weak attraction to the wall that allows them to cling to it. Okay, and so those are called van der Waals interactions. So they're very weak interactions between molecules, and it's just due to temporary charges attracting atoms that are very close together. Okay, so we went through our basically 4 chemical bonds. So 2 of them are within molecules. So the ionic bonds, those are weak, where we have 2 ions coming together to kind of share or give or receive ions or electrons, excuse me. We have covalent bonds. Those are strong bonds where they're sharing electrons either equally or unequally. We have hydrogen bonds that are between 2 molecules. They're weak interactions. And then we have van der Waals. That's just an attraction of temporary charges between atoms. All right, so here's a review question. Which type of bond represents a weak chemical bond? Would it be a hydrogen bond, an ionic bond, a covalent bond, or a polar covalent bond? Well, I would definitely scratch the bottom 2, right? Because covalent bonds are strong bonds. So ionic bond and hydrogen bond. So weak chemical bond. So which one of these 2, the hydrogen bond and the ionic bond, are chemical bonds? Is a hydrogen bond a chemical bond? No, that's just a weak interaction, right? It's not forming, it's not forming a molecule. So the ionic bond is a weak chemical bond. So that's the correct answer. So that's a tricky question because you kind of think, hey, couldn't it be hydrogen bond too? No, so hydrogen bonds are just weak interactions between two molecules, but a chemical bond is what's forming a molecule. Okay, so there's a little trick there. All right, so that's it for section 1.4, the building blocks of molecules. So by now you should be able to describe the structure of an atom. So, also, think about the subatomic particles as well as those, how the electrons can be configured in those shells. Describe how several bonds arise from the interaction of atomic particles and resulting charges on elements. So you should be able to describe the ionic bond, the covalent bond, and the hydrogen bond. Okay, so we're going to finish off chapter 1, Introduction to Biology, with learning about something that, as far as we know, every living thing needs, which is water. So we're going to learn about water in our last video.